We are going to cover actually uh, uh, not one topic but multiple topics. Give me a moment, please. Okay, so the first uh, thing that we are going to show you I think before explaining the materials, theoretical materials, let's see a few ideas in Mathematica first. For example, let's see how nested for work. First of all, let me write a matrix, a 3 by 3 matrix first. For example, 1, 2, 3, 4, 5, 6, 7, 8, 9. Technically, this is the 3 by 3 matrix, as I explained in our last class. And if we can even see this in matrix form, as far as I can remember, the command for that is / matrixfor in matrix form. So yeah, I think I should increase the screen size a bit. Okay. So technically, as you can remember, A is actually a set of sets. But technically, since this is a set of sets, and we know that a set of sets is actually any multidimensional set is technically a matrix, right? And we can nest even further. But for now, let's stick to a 3 by 3 matrix. Okay. Now, since I have converted it into matrix form, implementing further manipulations on this state is going to be tricky, because, for example, we have seen that if you want to access the first row, you can just write A1, but this no longer works because we have converted into matrix form. That is why I'm removing this line. Now A is just a set of sets. And if I run A1 now, it gives the first element, which is the first row, right? So matrix form is technically for our visual only. To work on the set, we need to keep it in the set of set format, right? Now, we can run a for loop, I equals to 1, I less than equal 3, I plus plus, another for loop. So technically, as should be able to recall that there are 4 arguments for the for function. I'm calling it function because it works like a function in Mathematica. So the first argument is the initialization. The second one is the condition. The third one is the increment, and the fourth one is a statement. Whatever statement you can write multiple statements here within second bracket. I'm writing another for, a nested for. I'm just writing j equals to 1. J less than equal 3, J plus plus, and here let's just write in the statement, just write print. And what do I want to print for now is the I comma, I forgot the syntax. How does it work? I think it works like, oh no, it doesn't work like that. I comma j. There is a missing, okay. So as you can see, for I, first of all, we start with I equals to 1. And for I equals to 1, since 1 is less than 3, the condition is true. So the statement is executed, and the entire statement is highlighted here. The entire for statement is the statement for just I equals to 1. So for just I equals to 1, the nested for runs from j equals to 1 to 3, and it prints A1, 3. A1, j for j equals to 1 to 3. Since we are fixing the first index 1, I equals to 1 here, it means we are accessing this first row only, right? And j equals to 1 means this guy, j equals to 2 means this guy, j equals to 3 means this guy. Now, if you increase I by 1 using this increment statement, I becomes 2. And this entire nested for statement runs for I equals to 2 again. And this time, we are fixing I equals to 2 here, and j runs from 1 to 3. So for I equals to 2, we are accessing the second element of the matrix, of the set. And since j runs from 1 to 3, j equals to 1 means this guy, 2 means this guy, 3 means this guy, and so on. Hence, we are just getting all these output serially from 1 to 9. So this is the same idea of nested loop from other languages, right? We have discussed this in Fortran, and you have worked with such nested loops in Python multiple times throughout your university life, right? So this should not be anything new to you. Just for Mathematica, this is a very compact, nice looking line. Now, all right, so in today's today, all the topics that we are going to cover today belongs to linear algebra. All right, so we are going to use matrices a lot in today's lecture, and hence I have showed this idea of accessing individual elements of a square matrix. Now let's get back to the PDF. Okay, the first idea is diagonalization. I think you are already familiar with the idea of diagonalization from your linear algebra course. A short recap. Say you have a matrix A, and somehow you were able to find another matrix B, so that A and B are related to each other with this relation, where P is a third matrix, and the only condition on P is that it's invertible, because we have P inverse here. And of course, P is a square matrix, because otherwise you wouldn't be able to have the inverse, right? So that's implied already. Now, in such cases, we say that the matrices A and B are similar to each other. Sometimes for similarity, we use a symbol like this. Some people like to use the conjugacy sign like this. The symbol doesn't matter, the idea does. So this is what a similar matrix is. In case you can find a matrix P, in case you are able to find a matrix P so that this B matrix is diagonal, that is, it has non-zero elements only in the diagonal, all the other elements outside of the diagonal are 0. In such case, we say that basically this is a situation where we can safely say that A is similar to a diagonal matrix. If A is similar to a diagonal matrix, we say that A is diagonalizable. And by diagonalization of a matrix, we mean that for a square matrix A, we actually search a matrix P so that P inverse AP becomes a diagonal matrix. And why do we need such a process called diagonalization? It has multiple advantages. A very silly advantages like this. For example, if you are to calculate a very high power of the matrix, it's computationally very complex, right? It's very time consuming, but if you are able to find a matrix P so that A becomes a diagonal matrix after being sandwiched between P and P inverse, then we can write P inverse AP equals to D. And what we can do is simply take 100 as the power on both sides. So what we have is P inverse AP, P inverse AP, and so on. And on the right hand side, we just have D to the power 100. Now, as you can see, all these pair of P's and P inverses gets cancelled out. Those are in between the string, except the first one and the last one. So finally, what we get is P inverse. Okay, yeah.
Question, sir. Sir, A to the power 100, স্যার এটাকে তো স্যার আমরা হচ্ছে মাল্টিপ্লাই করে দিতে পারি, মানে হচ্ছে কোডিং এর মাধ্যমে। সেখানে আমি কেন হচ্ছে এটা,
as I have already mentioned, that is
হ্যাঁ, একটু
Fahim actually
কনফিউজ আছে আর কি।
asked Fahim actually asked a good question. Why do we need anything other than just multiplying a with itself 100 times? As I have already mentioned, this is computationally very, very time consuming, right? Computationally very complex. It uses a lot of resources in terms of computer memory and a lot of time as well. But instead, we are developing a very straightforward method. Please stay with me. You will eventually see the advantage of it. So what we have in between is a to the power 100, p equals d to the power 100. And by multiplying a p on the left and by a p inverse on the right, what we get is a to the power 100 is p to the power, no power actually, p times d to the power 100 times p inverse. Now, as you can see, calculating higher power of a diagonal matrix is very simple, right? Just put the power of the diagonal elements, that's all. If you have a matrix that looks like this, if you take the power, take 100 power of this matrix, what you have is just 100 here, 100 here, and 100 here. So taking powers, high powers of a diagonal matrix is not that much computationally complex. And all we have to do is multiply these three matrices to get a to the power 100. So this is just a very silly example. There are multiple theoretical advantages as well in many places. For example, uh, uh, similar matrices, if you studied the theory of linear algebra thoroughly, you would get that similar matrices have the same set of eigenvalues. So if you diagonalize any matrix, then at the end you will get a matrix D that is a diagonal matrix, and conceptually it should have the same eigenvalues as A. But you also know, and you should also be able to understand that the eigenvalue of any diagonal matrix is just the diagonal elements. So technically, you know that after diagonalization, you will finally end up getting a diagonal matrix where the diagonal elements are just the eigenvalues. So theoretically, we have many advantages. This is just one silly example in terms of coding that I wanted to show you that diagonalizing is something that can be beneficial to us. All right. So how do we, what are the steps of diagonalizing an n by n matrix? Basically, what you need to do is just calculate the eigenvalues, evaluate the eigenvalues or find the eigenvalues, then find the corresponding eigenvectors. Then the P matrix is simply a matrix that contains the eigenvectors as columns. Now, for any eigenvalue, you generally get a corresponding eigenspace. You do not need the entire eigenspace. You just need the need a number of vectors from that eigenspace only. How many? The number of vectors we are going to extract is equal to the dimension of the eigenspace. So technically, if your eigenvector finally looks like this, for example, S110 plus T010, then since you can clearly see that the spaces eigenspaces dimension equal to 2, so all you need is two mutually independent, linearly independent eigenvectors. One is this one and another is this one. You're just taking s equals to 1, t equals to 0 once, and then taking s equals to 0 and t equals to 1. So let me show you by an example, already worked out example in the next page. Here you have we have a matrix A, 3 by 3 matrix. You know how to find the eigenvalues, right? Just simply formulate the characteristic equation and solve it for lambda. So the values of lambda are the eigenvalues. One of those values is 2, the other one is 1. 2 is a repeated eigenvalue, and for 2, you get an eigenspace that has two linearly independent eigenvectors P1 and P2. And for lambda equals to 1, you get one eigenvector. What you do, just make a third matrix P, a second matrix P, of which P1, P2, P3 are the first, second, and third columns. You can change the order also. You could choose P2, P1, and P3. The order doesn't matter. If you change the order, what happens is at the end, the final expression contains the diagonal element in different order only. If you change the order of the vectors here in the three columns, order of these three guys only change. That's all, nothing more. So this is a verification step where if you use this particular P matrix to find P inverse AP, after multiplying these three matrices, finally you get a diagonal matrix, and in the diagonal, the elements are none other than those eigenvalues, lambda equals to 2 and lambda equals to 1, 2 repeated twice. Okay, so this should have been already covered in linear algebra, but this was just a short recap because in case some of you forgot the ideas. Is there any problem so far? And Fahim, were your questions answered? Are you convinced with my answer?
Yes, sir. Yes, sir.
All right, okay. So we have another burning question. Is every n by n square matrix diagonalizable? And the answer is no. If the matrix is not diagonalizable, what you get at the end is less than n independent eigenvectors. So here's an example for you. Just like the previous matrix, you have two eigenvalues, one once and two twice. But if you, just like before, if you find the eigenspace for corresponding to lambda equals to 1 and try to find an eigenvector, you get this P1. But last time we got two independent vectors for lambda equals to 2. But in this case, the eigenspace corresponding to lambda equals to 2 is a vector space of dimension 1. So we can get only one independent vector. So in such cases, you are short by at least, in this particular example, you are short by one vector, one column. You are short by one column to formulate the P matrix. Whenever you are in a situation like this, you will understand that, okay, this particular matrix is not diagonalizable. But I think there is a shorter way also. All you have to do is, if you want to check if, before starting the process of diagonalization, if you want to check if the matrix is diagonalizable beforehand, all you have to do is apply the process called Gaussian elimination. If you apply Gaussian elimination, you will see that you are not going to get an identity matrix after the Gauss-Jordan elimination. The reduced row echelon form is not going to be an identity matrix. And in case for a square matrix, if the final row echelon form is reduced row echelon form is not an identity matrix form, we understand that there is at least one row short. There is at least one vector short, which is causing the linear dependence. All right, so there are two ways you can check if a matrix is diagonalizable before even starting the process. The next second topic we are going to cover today is the Gram-Schmidt process. If you have a set of a short recap again, if you have a set of R number of vectors, which is a basis to some vector space, for example, maybe the vector space is, the name of the vector space is B, for example. If these guys span the vector space B, actually not only span, but linearly independent. So if these guys form a basis for B, there is a possibility that in most cases, they are not going to be orthogonal. What I mean is a set I, J, and 2K, these guys forms a basis for R3, right? These guys form a basis for R3. But I can also write I, J, and I plus K. These three also form a basis for R3. But the first example is advantageous to us. The second example is not so much. Why? Because in the first example, the vectors are orthogonal to each other, which gives us a very nice shape, perpendicular, three perpendicular exist to each other, right? But in the second example, these guys are not perpendicular to each other. So I don't think I have to explain why perpendicular axes give you advantage, right? So we might be interested in converting this set of R vectors into another set of R vectors where they are still a basis for the same space, and also they are additionally that they are orthogonal to each other. In short, we say that this is an orthogonal basis. This is the idea of orthogonal basis. But how do we convert a given non-orthogonal basis to an orthogonal basis? There is an easy step for that. The concept is also pretty easy, and it's called Gram-Schmidt process. That is, for example, if you have a vector, say A, let's call it U1, and if you have another vector U2, and say we have just two vectors, the idea is these two vectors are linearly independent because they are not parallel to each other, right? Checking linear independence of only two vectors is pretty easy. Just you can see that they are not multiple of each other, that is, they are not parallel, so they are linearly independent. Now, just consider this U1 equals to V1, and form, instead of U2, form another vector, try to find another vector V2 so that V1 and V2 are mutually perpendicular. And how can we do that? It's pretty simple, actually. Just find the projection of U2 on U1. I mean, not just projection, but find, at the end, we need the component of U2 along U1. And what is the component of U2 along U1? Is the dot product of U1 and U2 divided by U1 magnitude square times U1. So if you just subtract this component from U2, imagine U2 to be divided into perpendicular orthogonal components. Call this guy V2. So how to find V2 from U2? All you have to do is just subtract this component from U2. What you get is V2, because simply U2 is V2 plus this component. I just transferred the component on the right hand side. So this is the exact same expression here, and you can see that instead of dot product, they wrote inner product, which is understandable because not every space is Euclidean Rn, right? So we are formulating a general formula for any inner product space. So that is why it's better to use the inner product symbol. But for our case, in today's lecture, we are going to stick with vectors over real numbers. So Euclidean space over real numbers. So that is why we can simply use read it as dot product if you want. Now, in the same way you got V2, you can just find V3. Just subtract the components of V1 and components of U3 along V1 and U1 and U2, and you are done. V1 and V2, sorry. So finally, what you get is a vector which should be perpendicular to V2, because you subtracted all the components that you needed to subtract. In this process, if you keep going, you end up getting a set of R vectors V1 to VR, which are mutually perpendicular to each other. Pretty simple concept behind this apparently complex looking algorithm. The concept is pretty simple. And in case you're not satisfied with just orthogonal basis and you need orthonormal basis, all you have to do is normalize the vectors VI. And how do we normalize vectors? We just divide the vectors by their magnitude. And for our lecture today, we are going to denote the orthogonal basis vectors by VI and orthonormal basis vectors by QI. So that this is the symbol we are going to use throughout today's lecture, whenever I use them. So here is an example, solved example, to demonstrate the Gram-Schmidt process. You have three vectors U1. Am I recording? Oh, yes, I am. U1, U2, U3, three vectors. They are linearly independent, and we do not even have to check that because they have this special format, which shows that they cannot be linearly dependent. So anyway, the process is just using the formulas. V1 is simply U1. V2 is U2 minus the component of V1 along U2. You get this vector, and do the same for V3. Just in this case, you are subtracting two components, this and this. Those who are skilled pretty well in linear algebra, you can understand that basically what we are doing is we are subtracting the component of U3 in the orthogonal space to the original space so far formed up to this point. So the concept of WT, generally the notation we go for in this case. Not really T, but this is
Sir, what do we mean
opposite of
by PROJW1?
projection of U2 along W1. Is that clear?
Yes, sir.
Okay. And for coding purpose, for those who are not that skilled in linear algebra, you do not have to go through the concepts every time. You can just use the formula of graphic process blindly, and you will end up getting the correct result. In case you are not that confident in linear algebra. And at the end, at the process, they normalize the vectors v1, v2, v3 to get q1, q2, q3. The next topic I'm going to cover is called keyword decomposition. Now, here is an interesting thought written in the form of a problem. Say, for example, you have an m by n matrix, and all the column vectors are guaranteed to be linearly independent. Someone take them for you, for example. And you considered those column vectors to be ui, and you applied the Ground-Smith process to get the vi's. In fact, you normalized to get the qi's. And now you formed a new matrix, which is also m by n, called q, that contains the modified versions of ui. So the original columns were vectors which were, since they were linearly independent, they were basis for the corresponding space, but they were not orthogonal. But the QYs are not only orthogonal, but orthonormal. Now, it's obvious that the matrix with UIs as column, which is the original matrix A, and the matrix with QIs as column, let's call that Q, these two matrices are related to each other by some relation. And of course, that relation is going to be linear in nature, because all the process we used in between is a linear process, right? So what is the relation between them? This could be a burning question. In some of you might have the question in your head by now. Now, this is how we do this. This is how we find the answer to this interesting question. You can understand that we can just write, since QIs form a basis, orthogonal basis, we can just write any vectors in that space which is spanned by the QIs by using a relation of this sort, where these guys are the projections. And maybe you have a question why there is no norm of q1 square in the denominator, because the vectors are normalized already, the norms are already 1, so that we do not have to worry about the denominator. So these are the projections, and these are the component along q1, q2, q3, etc. So you add this works like 2i plus 3j plus 4k. This I, j, and k are orthonormal basis vectors. These are exactly q1, q2, q3, etc. And these 2, 3, and 4 are the components along those rectangular coordinate vectors, just like these inner products here. These are the components, projections, I mean. So since the UIs are also in the space spanned by the QIs, that is why each of these UI can be expressed in such a manner as well. Now you have n equations here. This n equations which are linear in nature, can be easily written in matrix form, just like this. And after writing this in matrix form, you can see that this is just the Q matrix. This is the left-hand side, which is just the A matrix. So we have some new matrix that arise as a byproduct of the process, and let's call this matrix to be R. So you have a relation like this, A equals to Qi, and this is the relation between A and Q. But the question, new question now is, who is this R? I mean, this is just a third party, a third person, a third matrix that we end up getting it, right? But this matrix is little interesting, a little more interesting than that. How? These are the exact components. So these are the components of the UIs along the QJs, first of all. And second of all, another interesting is, can somebody tell me what the value of this guy is? We know the numerical value of this guy that I circled. Can anyone tell me? Since we have already orthonormalized, and U1 is simply V1, and V1 is simply Q1, just multiplied them by the magnitude of V1. So this is a scaled version. In terms of direction, this doesn't matter at all. This contributes nothing. So V1, direction-wise, V1 and Q1 are same. In that sense, this is in a way Q1.Q2, just a scaled version of Q1.Q2. And what is Q1.Q2? We have normalized, orthonormalized the set of vectors. So Q1 times any of the other Qy's is going to be 0. So that is why this guy is equals to 0, and so are all the elements below this guy. All of them are going to be 0 because all of them are going to be Q1 dot any Q. They are all just Q1 dot Qj, where j is not equal to 1. So technically, the conclusion is, except this guy, all the other element in the first column is going to be 0. And same can be said about, except these two guys, all those below them are 0. So technically, at the end, all of the guys below the diagonal is going to be 0. All of them are going to be 0. And eventually, we are going to get...
Sir, U2 Q1 টাও 0 হতো না?
Not really. U2 and Q1 is not going to be 0 because U2 is U2 is somebody else. Do you remember this graph? U2 is completely someone else. Q1 is somewhere along this direction, which is exactly in the direction of Q1, exactly in the direction of V1. And V2 or Q2, both of them are in this direction. This is the direction for either V2 or Q2. They are not same, but they have same direction. But U2 is somewhere here. That is why none of the guys in the upper triangular area is going to be 0. The process, just look at the formula in the process, okay? In the Gram-Schmidt process, what you get here, you use the vector in the immediate step that is you're following to get the orthonormal vector or orthogonal vector. You're using the one above to get the one below, not the other way around. That is why those are, that is why the Qi's with the Qi dot uj is 0 for I greater than j. Once you are guaranteed that you got the earlier Qis and you just got a new Qi, this Qi is going to be perpendicular to all those above it, right? All the Ui's above it, but not the other way around. Am I clear?
I think.
Okay. I think I could have chosen better words to explain, but I think you can give it a go after the class. You will be able to understand clearly. Okay. So technically
একটা কোশ্চেন
our
এখনো আছে
sure sure
আচ্ছা, অর্থগোনালটা আমার কেন লাগতেছে মানে একটু ভুলে গেলাম জিনিসটা একটু কনফিউজড মানে
your
অর্থগোনালি
question.
আমরা নিচ্ছি কেন আসলে
Okay, why are we interested in finding orthogonal vectors? This is something I already explained at the beginning. Just imagine R2. R2 can be thought of a space spanned by I and J vectors, the well-known I and J vectors. But it can also be thought of a vector space spanned by I and I plus J. Because both of this set have dimension 2, both of these set have linearly independent guys, and any vector in R2 can be expressed as a linear combination of these two as well as these two. So they both of these set actually fulfills the conditions of basis. But for the previous case, for I and J, for the first case, you have a unit vector here and a unit vector here. But in case of the second case, not unit vector, basis vector, but kind of works like unit vector. That is why, I mean, this vector is not normalized, so I cannot really call it unit vector, but you can understand it. They are kind of similar for the purpose here. So I is here and I plus J is here. So technically, whenever you have a point here, or whenever you, let me use another color for this. Whenever you have a vector here, you can express it as a linear combination of I and J. Just count the number of I's you got here. For example, you have a number of I's here, and perpendicularly you have to take B number of steps vertically. So finally, you can express this vector as AI plus BJ. But in this case, for example, if you have a point here, so if you want to express this vector as a linear combination of the basis vectors in this figure, what you have to do is, this is the number of steps, for example, say C, and the number of steps along this not perpendicular line, inclined line is, say, for example, D. Then you can just write the vector as CI plus DI plus J. Just tell me in plain one word, which one do you prefer more, the upper one or the one in the at the bottom?
বটম পার্ট
You like the bottom one? You want to use the bottom one for expressing every vector?
না স্যার আপার পার্ট স্যার
Okay, this should be the, I mean, there could be some guys who prefer the one at the bottom, but in general, we like things perpendicular, all right? So, most of the normal guys I know would go for the one at the top. So, this is why perpendicular vectors are useful to us, because
স্যার আপার পার্ট একেবারে মানে ভেরি ইউজফুল এন্ড সেটা হচ্ছে মানে
easier
ইজিয়ার
to comprehend, easier to manipulate, easier to use,
কম্প্রিহেন্ড
right?
এক্স্যাক্টলি
Exactly. That is why we like our basis vectors to be perpendicular to each other. Okay. Now, here is an example. Those same vectors we used earlier to carry on the Gram-Schmidt process. Now, the process of QR decomposition is straightforward, right? First of all, you have to find the Q vectors so that you can formulate the Q matrix first. And that's straightforward because all you have to do is carry on the Gram-Schmidt process, apply them to U1, U2, U3, and you already got Q1, Q2, Q3 in our earlier example of Gram-Schmidt process. So use them as a column to formulate the Q vector and you're done. So this is the Q vector you can see just by using the Qi's as column. And for R vector, all you have to do is take these dot products. And after taking these dot products, you formulate the R triangular looking R matrix. And if you want to verify, you can just multiply Q and R. You will end up getting A if you do not make any mistakes during the calculations. So that is what keyword decomposition is, or how it's done for a square matrix n. Please let me know if there is any question. Otherwise, I'm moving on. This is the last topic we are going to cover in today's lecture, and the topic is called orthogonal diagonalization. We already covered diagonalization. I have already mentioned multiple times. I'm mentioning again. All of these were covered in the linear algebra class, right? This is just a recap. So in case of diagonalization, we dealt with a concept called similar matrix, right? A is similar to B matrix if we can find a matrix P so that A and B can be related to each other using the help of the matrix P like this. And if B is a diagonal matrix, if there is any P that makes B to be diagonal, then A is called diagonalizable. And the process of finding the P is called diagonalizing A, or diagonalization of A. Now, there is a very similar concept, but first of all, to define that concept, show that concept, we have to define what an orthogonal matrix is, and it's a very simple concept. If the transpose of a matrix is exactly equal to the inverse of a matrix, we call that matrix orthogonal. And if a matrix is orthogonal, then A times A transpose or A transpose times A, replace A transpose by inverse, and you will end up getting the identity matrix. The definition is pretty straightforward. Now, in case of similar matrices, the relation was B equals to P inverse AP. But if that P matrix is orthogonal, then writing P inverse or P transpose won't matter much. So if you can find an orthogonal matrix P so that B is related to A like this, then A and B are not only orthogonal, or not only similar matrices. Because of the speciality of P, we call them orthogonally similar. Just one adjective more than the previous idea. And the process of orthogonal diagonalization is almost pretty similar to the previous one as well. The only difference is, in the earlier case, after finding all the eigenvectors, we applied the Gram-Schmidt process on them to find the P matrix. But in this case, not really Gram-Schmidt process, right? What we have to do is just find linearly independent eigenvectors and construct a matrix P by using those eigenvectors as column matrices, right? That was the only idea. No orthogonality involved there, but now orthogonality is going to play a role here. In this case, what you do is, give me a moment, please. Okay, in this case, what you do is first find the eigenvectors, linearly independent eigenvectors for one of the eigenvalues. For example, these two are for corresponding to, these are eigenvectors corresponding to lambda equals to 2. So we can understand that while finding the eigenvectors, the eigenspace was found to be having dimension 2. So we were able to find two linearly independent eigenvectors. But before finding the eigenvector or eigenspace corresponding to lambda equals to 8, apply Gram-Schmidt on U1 and U2. And after applying Gram-Schmidt on U1 and U2, you get V1 and V2. And then actually applying Gram-Schmidt process for only two vectors is pretty simple, right? Because the formula gets complex as we move on to the next vector. But here we have just two vectors. So this was a simple one. The next one will be even simpler, because for lambda equals to 8, we got just one eigenvector. Applying Gram-Schmidt process to it means nothing. It just means V3 equals to U3. The only difference between U3 and V3 here is that they already applied the normalization process also after applying Gram-Schmidt, but they denoted it by V3 but not Q3, but I think you should be able to understand. So now we have an orthonormal set of vectors V1, V2, and V3. Make a matrix P having them as column vectors. Now we are done. And the verification process in this case is even easier than the last one, because for the last one, we had to find P inverse. For the last one, we had to find P inverse here, but here all we had to do is transpose the P matrix and multiply these three to get a matrix that is exactly diagonal. And just like the last time, we have the eigenvalues here. Now, there is an interesting idea. Can you see that the matrix they used here is a symmetric matrix? The matrix is symmetric. Its transpose is exactly equal to itself. Now, is this a coincidence? The answer is no, this is not a coincidence. If you have a relation like this, D equals to PTAP, if A is orthogonally similar to a matrix which is diagonal, we call A is orthogonally diagonalizable. That was the definition, right? So if A is orthogonally diagonalizable, we should be able to find an orthogonal matrix P so that we can relate A to some diagonal matrix D in this way. If you just take, first of all, I mean, let's just take transpose on both sides. D transpose is P transpose A P whole transpose, and we know that transpose operates in opposite direction. It reverses the order. So we have P transpose, A transpose, and P transpose transpose. So we do not have to write transpose twice. We can just write P. Now, what is D transpose? Since D is a diagonal matrix, it's transposed itself, right? So it is the transpose of itself. So D transpose is simply D. And in case of D, we can just write this guy. So P transpose AP. So you have P transpose AP. Let me write again. P transpose AP is exactly equals to P transpose A transpose P. And this is only two. You can do a few lines of calculations. Just replace P transpose by P inverse because P is orthogonal. And multiply by P on the left, multiply by P inverse on the right. Finally, eventually, you would end up getting this interesting relation. So if we were to find some P matrix that does this miracle, the matrix A we started with must be a symmetric matrix. Otherwise, this will not work. Otherwise, we will not be able to find a P that satisfies this kind of relation. So the matrix that we want to orthogonally diagonalize must be a symmetric matrix. If the matrix is not symmetric, you cannot orthogonally diagonalize it. The time will be wasted. So that is why this A matrix was symmetric to begin with. Is there any question about anything anywhere in today's lecture so far? Okay. So now I am going to provide an assignment that will, ask you to do everything that we covered in today's class using Mathematica. So there will be a problem that will ask you to diagonalize a given matrix A, and you have to do this using Mathematica. How can you do that using Mathematica? First of all, go to help, and in the documentation center, just write eigen. I think that will do. Okay. So eigenvalues, let's write eigenvalues. So you can see that there is a function eigenvalues that will just give you the eigenvalues of a square matrix N. So in that way, if you construct a matrix like this at the beginning of your code and just write eigen. Why is it not predicting? Okay, eigenvalues of A. It doesn't work because I wrote capital A. So these are the eigenvalues of the random, not so random matrix I wrote here, consisting of all the integers sequentially. So this is these three are the eigenvalues of that matrix. Another function you got there was eigensystem. An eigensystem gives a list of values, eigenvalues and eigenvectors. And if you just write eigensystem here, and input A, it gives everything. So these are the eigenvalues, and these are the eigenvectors corresponding to those eigenvalues. The serial is maintained here. The first eigenvalue corresponds, the first eigenvector here corresponds to the eigenvalue here. And I have already taught you how to access the individual elements from this set of sets. For example, if you just write B equals to this guy, and if you are interested in, say, for example, this vector, so you should be able to see that we have a set of sets. The first set inside is a set of eigenvalues, and the second set of sets contain the eigenvectors. So all you have to do is find the correct index of B. So if you just write B3 here, okay, this is the first set, second set is, okay, there is no third element. This entire set is the second set. So just write 2 here, and this guy is the second of the second set. This guy is the second member of the second set. So just write 2 here, and you have what you want. So if you want to access these guys individually, you can do that. And if you want to extract these individual eigenvectors to construct a P matrix, you can do that as well. You have already seen how matrices work. You can even use loop if you want by actually saving these guys in another array. Say this is C2. If you just save this entire eigenvector in C2, and you can write similar lines, for example, I'm copying this and pasting this. So if you want to save the first eigen vector in C1, you have to replace these 2 by 1 and do something similar. Just write C3, where you need to save the third eigenvector, just replace these 2 by 3. So after all these, let me use semicolon so that I do not get individual displays, but rather I'm interested in a matrix C. What? Okay, I think I got it. I should have done this. All right. What's wrong with you? One minus two. Okay, who is this guy? Okay, C3 works fine.
So I think you
C3
need to shift enter every line so that every input is counted.
come again. I need to.
I think you need to shift enter every line. You shift entered after the third line, so it read the third line.
I don't think so, because all of them are packed within the same bracket. And in that case, Mathematica executes everything inside a single bracket. So that's not the case here. That could be a case here, but that's not. I think I am misusing the symbols. Okay, this can be done in better ways actually. So if you just write 3 different variables.
Sir, when do we use semicolons?
Okay, if you do not use semicolon, computer by default gives you output of that line. If you do not want that output, you just use a semicolon. That's it. No big deal. And form another matrix which has C1, C2, C3. This can be handled pretty easily. And if you there is a case that we need these eigenvectors as columns, but not. I forgot to write equal here. I need them to be as the columns of my C matrix. Okay, let's call this P matrix. And they are not columns but rows, so they are rows. So I think I need to transpose whatever I have here so that the eigenvectors go into the columns and not the rows, and we are done. And all right. Okay, so these are the stuffs that you need to deal with when you are going to need these stuffs when you try to diagonalize a matrix using Mathematica. It's possible that there might be a direct function for that because Mathematica technically has anything you think of. But I do not want you to use that function if it exists. I want you to follow the entire process. You do not have to do everything using element by element by running for loops. You do not have to solve the characteristic equation, formulate it first and solve it like you do when you solve analytically or mathematically, but at least use the eigenvectors or eigenspace commands to extract the eigenvectors and formulate the matrix using basic operations. And finally, you will need to verify that you have already actually successfully diagonalized the matrix A. And you can understand that all the questions that are going to follow this question are related to today's lecture, right? For example, I'm going to give you a set of vectors that you need to apply Gramsci process on. Then I'm going to give you a second task related to the same question to find the Q and R matrix for QR decomposition. And finally, you need to orthogonally diagonalize a matrix. So you need to apply the ideas of both of the problems I have discussed just now. The process of extracting the eigenvectors, etc., and the process of QR decomposition, combine them to find the orthogonal diagonalization of a matrix A. So you already know the assignment problems. If you want, you can just start coding right now after I end the meeting in a minute or two, or you can wait until I post the actual question about in 30 minutes or so. Please let me know if there is any question.
Sir, what's the assignment question? Like which particular question?
I just described the questions. I'm going to post it within half an hour anyway, but I just described the questions. The first question is going to ask you to diagonalize a matrix, a given matrix. The second question is going to ask you to apply the Gram-Schmidt process on a set of vectors. Exactly the ideas we described just now. Was it clear?
Yes, sir.
Can
Like, sir, you
share this
said
PDF?
that we can start working on it right now. So I thought you had given a specific question, like exact numbers to work with immediately.
For now, you can start with any random numbers. In the assignment question paper, you are going to get exact numbers. You can just edit them, right? Anytime. So for now, you start with your own matrix for now. Okay, and Najmul, Fahim, you are asking something?
Sir, can you share this PDF file?
Of course, I'm going to share this
Grams
PDF file.
per- Yeah, okay.
Okay. All right. Any more questions? Okay. Thank you for attending the class. Today was probably our last class. Let me end the meeting. First of all,